Everybody, let's do second part for this video about centripetal acceleration. So in the first part we proved that A equal to V squared by R, that means the relationship between A, V and radius of the circular path. And today we are going to do the same thing in different way so that we can visibly and geometrically see the direction of acceleration is towards the center. And this is the reason why this sort of acceleration here is called centripetal acceleration. And also, in addition to the centripetal acceleration, we'll also see that what is called the centripetal force. So definitely, if you are considering something towards the center, like we saw if you see the direction of acceleration is directed towards the center of the circular path, that means we can also say that the force on the body also acts directed towards the center, and that force will be called the centripetal force. Let's try again the relation A equals to V squared by R, or you can say this as R omega squared also, and you see that this is directed towards the center. Center means the center of its circular path. So in order to do so, let's draw a circle. Drawing a circle. Draw a circle means what we are doing here. Somebody is moving in a circular path about some fixed point. We call this as A, due this direction, for example, with velocity V or speed V. And then this tangent line vector represents the linear speed at the point where it is tangent to. You will see, and at this particular point this velocity is linear, and you can just represent this by vector V, and then at this time we see the magnitude and direction of the given velocity vector. So in general we call that as V, having both magnitude and direction. And if you join these two lines, you have already seen in the previous class that this line will be 90 degree, and also from geometry, if you see, this is a line, that is a radius, and when it meets a point where another line is tangent, then the tangent line and this radius line, we call it as R, they are 90 degree to each other. Now in a very small time, say that time as delta, okay, you can call that time as delta t. Alright, so in a very small time delta t, suppose that this particle is at this point and describing a velocity v in both magnitude and direction. At this particular point, you can call this point as B, and whenever it changes the direction from position A to position B, it traces out or inscribe the angle by del theta. So here we are using the term del theta, del t. That means there is going to be very small change in the sort of thing that have been acting over here. So here at this point, now let's talk about for this point, suppose that as del theta t is very small, that means A and B are very close to each other. Alright, so in a very small gap of the angle change, and also in a very small time, you can say that A and B, they are very near to overlap to each other. So in this case, what we call this A as the initial position of the particle. Okay, and B as the final position of the particle. For a while, there are a lot of initial and final positions. There might be like this. Alright, so we consider some particular points to see that how acceleration equals to v square by r, and also how does it act towards the center of this circular path. And here you should note that these two velocities are not the same in fact. Alright, so the velocity is in fact that is not the constant. Alright, what is constant? The motion of the body, that means the change in direction of the motion is constant here. Alright, so we should keep into mind. So in order to find some sort of initial and final position sort of thing, so suppose that this is V. Now let's take a line parallel to the tangent line at point A. And from your previous video also you know that this angle is going to be del theta, because this is also 90 degrees to the tangent. So if you consider any line parallel to A, for example here, okay, so I am taking this line reference to this line with reference to the line through A. So that because these two lines are parallel, and between these two we are just considering the angle between these two vectors at A and at B, and this is also a straight line, so this is angle del theta, this is also going to be angle del theta. Alright, now let's consider the horizontal and vertical component of velocity at this position. So here horizontal means what you have to take, we have to take the component of the velocity parallel to the vector v. So this vector v, so that means it is v cos del theta. So its horizontal component or the component parallel to the initial vector v is in fact v cos theta at this point. And perpendicular component, that means the vertical component for this velocity, can you tell me? Because when you take horizontal as v cos del theta, what is the vertical component? Vertical component is in fact it is v sin theta, that means del theta. It's okay? Now as del t tends to 0, that is it's a very small time, the del theta tends to also 0, that means itself is very small. You see that as if B and A coincide to each other. It's okay? So that this perpendicular line and this line will be parallel. Here you can see here it is perpendicular, this is also perpendicular, so that you see that this is the position for v sin del theta. Alright? Okay. Now let's talk about initial and final position. You know that, so firstly you consider along what you call along the direction parallel to the vector line B at A. So at this point, what you can see here, acceleration at this point will be, you know that acceleration is change in velocity by change in time. So here at this point, the change in velocity means definitely we will think for the difference of final velocity and the initial velocity divided by time in general. So for this situation, let's see that if A is the initial position and B is the final position, so final velocity along the line parallel to the tangent at point A, or this vector at point A, is v cos del theta and minus, initially it was v So divided by the change in time, that means very small change in time as delta t. Now here, what you can see, like at this point when your delta t tends to 0, that means t is going towards 0, for example, what is happening to this? Del theta will also tend to the value 0. So in that case, automatically the del theta also tends to the value 0. So then what is going to happen to this cos del theta in this case? It will tend to 1, because if theta goes near and near to 0 and at point 0 it will be 1. Therefore, if theta tends to 0, that means cos theta is going to be 1. So in this case, you can see like this would be v times of 1 minus v by d theta in general, and v minus v is going to be 0. Then what do you conclude that? It means the acceleration along this line is now 0. That means the acceleration outward of this circular path is found to be now 0. Then now let's talk about the vertical component here. So what you can write, you can just use the same language, like along the direction parallel to the vector v at A. What we write now here, what you can write now, next along the direction of the motion perpendicular to position, you can say position or point, position A. It's okay? So in that case, what you see, like perpendicular to at B is in fact it is the final position and this is the initial position, as del theta is very small, B and A are very close to each other in this case. So what can write here in this case is that acceleration will be, your acceleration in this case will be final speed is v sine del theta, and the initial acceleration, let's see here now. So this is in fact very close to this point. That means at this point what we have considered? We have considered the velocity, this velocity only, outside of this circle. However, due to some force, it is circulating. But what happening here? This velocity is towards the center of this circle. That means this is very close to, this line is very close to the line v sine del theta, and you see that its direction is towards the center. That means even if you find the change of velocity, in this case, for example, from initial to this position, the direction of your dv will be towards the center in this case, because of the reason that v sine theta is towards the center. So if the change in velocity, for example, dv is towards the center, that means acceleration acts along the direction of the change of velocity. And hence we see in this case towards the center at this point there is no velocity. That means this is 0, and divided by it is change in velocity by change in time, and time is here del t. Let's go further now about this. So at this point, what you can say, like as del t tends to 0, we have del theta also tends to 0, and hence from trigonometry and the geometrical condition of the limit theorem, hence we see that sine del theta in this case is very nearly equal to the angle del theta. It's okay? Alright. So therefore, what you see in this case is that acceleration, we call now this as A, and which is along the direction perpendicular to this vector, which by comparison acts towards this direction. This is very close to B, is very close to A. It's you can see that it acts towards the center, and the change of velocity due to the direction is also towards the center, and hence the direction of this acceleration is towards the center. So after that, what you see in this case is this case. So B, we are taking the constant in this case in general. So this is B. Now limit del t, and hence del theta also tends to 0, and sine this del theta by this is for the small, also you can take this is del theta and this is del t. So it is now V times of this sort of factor by definition of the first principle of calculus. You can write here in general d theta by dt, and d theta by dt is, in fact, this is, you know that d theta by dt is rate of change of angle, that is the central angle, and this is denoted by omega, which is called the angular velocity. And so after that, what you see here that V A equals to V times omega, and you also know that omega equals to V equals to R omega. So in place of omega, you can substitute V by R. So that in this case we have now it is V times of omega, means it is V by R. So it is V square by R. Alright, so what you have got now, therefore you have got it as, therefore you can say that A equals to now V square by R, and it acts towards the center of the circular path caused by the circular motion. And also you have seen that it is A equals to, you have also write in terms of it's also one of the kind of formula, A equal to V omega. This is also formula for the centripetal acceleration. Alright, so it acts towards the center of the circular path, hence this is called centripetal acceleration. Alright, and you can see this centripetal acceleration in the different form. Like firstly we have got here A equals to V omega, and after that we replaced V times omega equals to V by R. So we got it is V square by R. So this is another formula for the centripetal acceleration, and either use here or at this point also we can say here V means R omega, and this omega is already here, so another formula is now R omega square. So these are the formula to calculate the centripetal acceleration. Now let's talk about the centripetal force. Here you see there is the direction of acceleration is towards the center, and if you consider this particle of mass to be m, for example, yes, m for example, then you know that by Newton's second law of motion, F equals to ma, and then you substitute the value of A, then you will have the formula to calculate the centripetal force. So what you can say now after, by Newton's I think it is second one, like no first one, second one. By Newton's second law of motion, You know that is F equals to ma. So here, just earlier I discussed that the force acts towards origin in fact the force due to the acceleration, and the force is the product of mass and acceleration by Newton's second law of motion. You can use this formula F equal to ma, and F equal to ma means we have here m, and then a value you can take as any, firstly most popular or the first we take value v squared by r, that term v squared by r, so that is mv squared by r. Okay, so the formula to find the centripetal force is that mv squared by r. Why it is centripetal force? Because it acts towards the center, and this force acts in the direction of the acceleration, which is towards the center. That's why this force developed in that object is called the centripetal force, or the force applied on the subject on the object is called that centripetal force. And this you can also write in terms of, like, just to replace, it is m v squared means we have r omega square, and then r is already here, so that it is now, after this remove the square, so it is m r square omega square, and then by r and 1r cancel out here. So finally we have, in terms of omega, this is mr omega square, and the unit of the force is Newton.